regard to motion? Maybe. Okay. Work. There's all sorts of different ways to describe work. The symbol for work is a capital W. And we're going to talk about kind of linear work first. Yes? Oh, thank you. Much better. Work. One way I want you to be able to calculate work is by taking the force that's applied to an object, multiplying that by the distance over which the object is relocated. Okay, so work is equal to force times the distance. Right, so I've got some examples here. First off, we see somebody pushing a box. Okay, so it starts here, so I'll put this is I for initial, and this is F for the final position. So you could take, like they're doing, like where the edge of the box started and where the edge of the box ended, and that would be your distance. So all you got to do is take that distance times the force that guy applied. Not too bad. Does anybody remember what the units of force are newtons? The units of force are newtons. All right. So here's one for you. Here we have somebody in the muscle shirt. I'm sorry, you're outnumbered in here. I think the whole muscle shirt. Trying to push that wall. Of course, the wall's not moving. So what's the distance? The distance is 0. So whatever force he applies times 0 is 0. So 0 work is done here. Cool. So down here, I said that units of force are newtons. Units of force are always also kilogram meters per second squared. Oh my goodness. So I'll just kind of circle down here what I have here. Units of force are, yeah. So units of work then are units of joules. In the metric, it's joules, and in the English, it's calories. We've heard of calories before. You flip your candy bar over and you see how many calories. Basically, their candy bar calories are a little bit different. They're what we call dietary calories, but it's the amount of work that your body needs to do to consume those things that you've taken in. Like, I guess it's mostly carbohydrates and fat. Since force is a newton and distance, we said, is going to be meters, is the basic unit, work can also be Newton meters because it's force times distance. Makes sense. A lot of times working physical science problems, if you focus on the units, it'll take you down the road. So we can use units of Newton meters for work. We can also use units of joules for work. We can break joules down into what it means in little pieces, like of the scientific way of measuring things. It'd be kilograms, meters squared, and seconds squared in the denominator. Cool. So let's work a couple of problems. So feel free, if you're like, I bet I know what these work. I bet I know how to do these. Go ahead and do them. In the meantime, I'll kind of stand up here and kind of talk to myself or talk to you and do them all here too. All right. So if the man in the figure above pushes the crate with a force of 2.5 newtons, and he's going to relocate it a distance of 6.12 meters. How much work did he expend? So don't forget your units. So I'm going to do work is equal to force times distance. So the force was 2.5 newtons, and the distance that the object was relocated was 6.12 meters. And I'm counting, I count what, 2 digits here and 3 digits here, and I always go with the fewest. So I'm going with 2 digits from left to right, whatever I get. So I got 2.5 times 6.12. I got, my calculator said 15.3, but I'm only going to go with 1.5. So I'm going to go 15, and the units of work will be, I have some options here. I'll probably go with joules. I could go with joules or Newton meters or kilogram meters squared per second squared. I'm going to go J for joules. That's it. You could do one of those on the test, right? Okay. Oops. Next one. So now we're relocating at the same distance, okay? But we're going to push. Now we have to use scientific notation here. We're going to push with just a fraction of a newton. Instead of 2.5 newtons, we have 2.3 times 10 to the negative 6th. So work is equal to force times distance. So work is equal to that force I was applying, which is 2.3 times 10 to the negative 6th. Units are newtons there. And the distance was 6.12 meters. I have 2 digits here, and I have 3 digits here. I have to go with 2. So I have to remember how we do scientific notation. 2.3, my calculator, I hit the EE key, and I do negative 6 times 6.12. So I'm going to write what my calculator says. I'll write calc, because then I'm going to round it. What my calculator displays is 1.4076, and then I have an E, and then I have a negative 5. Okay, so what that is 1.4076 times 10 to the negative 5th, but I'm only going to go with 2 digits, so I'm going to keep these first 2 digits. I'm going to lop it off. So what I would say my answer is 1.4 times 10 to the negative 5th, and I'm going to go with units of joules again. As I was working this, are there any questions about that? 1.4 times 10 to the negative 5th. Now, on the test, if you're working this and you're like, hey, I think my units are newtons meters. And it kind of makes sense. A lot of times in physical science problems, you're like, does that make sense? Well, in this case, he applied more force to relocate the object the same distance. This is less force, so this makes sense. 15 joules versus 1.4 times 10 to the negative 5 joules. Okay. Less work was expended. Why do you think, you have any ideas why he only had to expend this fraction of a force to relocate the same object, maybe? Maybe the object was lighter. Okay. So maybe he put it on something that made it flow better. We don't know. All right, one more. How much work was should be spent, pushing with a force of 2.5 newtons, again back to the 2.5 newtons, but instead of going 6.12 meters, he's going to take it farther. So what do you think? Should the force increase? Yeah, I think so too. So work here is equal to force times distance, so the force is 2.5 newtons, and the distance is 12 meters. I'm going to have to round it to 2 digits. Oh, so my calculator displays a nice
round number. It displays 30. And the thing here is, and I'm not going to belabor it in this class too much, but if you take other science classes, they might tell you, if you're allowed 2 digits and you only have 1 digit like that, if I put a decimal right there, that goes ahead and makes that 0 special. Go ahead and do that. So now I have 2 digits. And what will my units be? Units of work. Joules. Yep, perfect. So any questions about this? It always looks so easy here. And again, it seems like your textbook makes things more difficult than it needs to be sometimes. But. Okay, so these problems will be due when we meet Wednesday. So page 104, essay or short answer number 2. And then page 106, exercises number 2 and number 4. And I have a hint, I believe associated with just number 4, that use W is equal to FD. Well, I want to talk about one more thing today. I actually have a little video to show you about energy. And it can get a little interesting, I think. But the guy pushing the box, okay, he accomplished work and he had to expend energy. And actually those two quantities are the same. Okay? So energy is either stored or capable of doing work. 2 types of energy, broadly speaking. I'm going to talk about different forms of energy, like electrical energy, chemical energy. There's gravitational energy, but there's stored energy or energy that's being spent. The stored energy is called potential energy, abbreviated PE. The energy that's being spent is kinetic energy. So as the guy was contemplating relocating the box, he had potential energy. Okay? As he was moving it, that was kinetic energy. And then as he got there, he still has more potential energy. Energy, actually then, units of energy are the same as units of work. So we're talking joules here. Remember, joules can be a Newton times a meter, or a joule can be a kilogram meter squared per second squared. Okay, so units of energy are joules or calories. Units of work are joules or calories. So this is what I said just a minute ago, that the work that somebody accomplishes is equal to the energy that they expend. Makes sense to me. So I kind of, it's sort of anticlimactic, and hopefully you guys took good notes, so help me out here. This is the same slide as we had a minute ago. All I did was cross through the word work and change it to energy. So here we go. So I'm going to go up here to the top here. I'm going to actually add, I'm going to say that energy spent in this case is equal to the force that was applied. Goodness, my pen's not working now. Is equal to the force that was applied times the distance over which that force was applied. That was the amount of energy expended. So in this case, energy spent is equal to the force that he applied, 2.5 newtons, times the distance over which it was applied, 6.12 meters. And what did we come up with? Oh, 15 joules. Did we buy that? I agree. Actually, it's on my calculator. My calculator's so smart. Next one. This was the one, oops, sorry. This was the one where we went ahead and backed off on the force. So now in this case, energy, not work, but energy is equal to the force that's applied, 2.3 times 10 to the negative 6 newtons, times the distance over which that force is applied. It's still that 6.12 meters. And remember, this is a case where actually we're allowed 2 digits, and we went with 1.4 times 10 to the negative 5th. Again, units are joules. So the energy spent is equal to the work accomplished. And last but not least, in this case, we went back to the first scenario, applying that stronger force, 2.5 newtons, over a farther distance than was originally, though. So in this case, the energy spent is equal to the force applied, 2.5 newtons, times the distance over which the force is applied. We're going to round it to 2 digits, and this is where I get 30. So I'm going to go ahead, and since I get 2 digits, I'm going to put a hardcore decimal right there. And of course, units of energy is the same as units for work, and that's joules. Not too bad. So here is where the video comes in. Let's watch the video first, and then I'll unveil that. But that basically summarizes a lot of what you just saw in the video. So energy can either be stored potential energy or energy that's being spent. So we call this potential energy waiting to be used. So for instance, those fries that they kept towing or whatever, when you have a candy bar before you eat it, it's potential energy. Specifically, it's potential chemical energy, energy that our body can, via chemical reaction, turn the inanimate stuff into energy for our body. That's what we call potential energy. The battery, as it sits on the shelf, little energy with your buddy. Okay. The person who actually is, you saw the bow and arrow, okay, that's stored potential energy, elasticity. The dude who jumped off with the bridge, bungee jump, or with a bungee cord, okay. We'll talk more about this when we meet on Wednesday, but just because of its position, an object can have stored energy. Like, for instance, I could let this thing fall, and since it's up here, when I let it fall, it's gonna go ahead and have kinetic energy. So just because of its position, it has stored what we call potential gravitational energy. Somebody running is actually spending some of those calories that they took in. So that is energy on the go, energy being spent. So we call that kinetic energy, energy associated with motion. Our fuel that we put in our car is another type of kind of fuel that we eat. Okay, it's again potential energy for our car. When we run our car, we do a lot of things. Among them, we create energy, thermal energy. Electrical energy is the energy associated with electrons that are on the move. Okay, so again, that's kinetic energy. When something, we'll talk a little bit more about this, especially in the last part in our physics, the idea that sound actually is a perturbation of air. Okay, so sound is actually a kinetic thing. When we hear something, it's because the molecules between what created the sound in your ears have been compressed in this kind of cool pattern, and our eardrum actually responds to that. It's just amazing. The last one I have up here is light energy. Again, sound and light energy we're going to talk about in the last part in physics, the physics.
So that's as far as I wanted to get today. So if it's okay with you, we'll call it a day. Let me know if you have any questions.
I figured it would be okay with y'all.